In this module, we will discuss basic vector operations. Keep in mind that a vector is a mathematical quantity which is then subject to certain rules of manipulation. In some cases, it works in a similar way as a scalar number. In other cases, it's quite different. So the first operation we'll examine is scalar multiplication of a vector. For example, suppose I have the vector 5 meters northeast, which is drawn with that diagonal arrow, and I want to multiply that vector f by the number -2. And I can do that, and my result will be -10 meters northeast. The idea being that I multiplied -2 by the scalar 5 meters, which equals the scalar -10 meters, and then that -10 meters applies to the same original direction that we had. On the other hand, as we saw earlier, I could write that same vector as +10 meters going in the southwest direction, and both of those are equivalent. But the idea is it's possible to take a vector f and multiply it by a scalar. In particular, you can negate a vector by multiplying by -1, and that's a common operation we'll use sometimes, especially when we start subtracting vectors. But a special case of negation is multiplication by -1. Now I'm going to have you think about this, but suppose I ask you, what do you think is the relationship between the magnitude of a vector f and the magnitude of a scalar k multiplied by that vector f? And k could be any scalar, including a positive or a negative. Think about what this would mean. And we might talk about that in class. Could you write down a relationship of the magnitude of f and the magnitude of k times f? Maybe take out a piece of paper and a pencil and start thinking about that. Okay, vector addition, also called getting the vector resultant or sum, is an extremely important topic, and in fact it's the basis of our first test in this class. So we're going to first do this geometrically using what's called the head to tail method. And suppose we have two vectors, one is called A, one is called B. And let's say on the left I draw the vector B, on the right I draw the vector A. The resultant of A plus B can be constructed by first doing A and then doing B. So for example, what that means is I'm going to draw each vector in a sequence, but to do that, I'm going to first give you some new terminology. The part of the vector where you see the arrow is called the head. The opposite side of the vector is called the tail. Sometimes also you can use the word tip for the head, the word base for the tail, but either way, there's two parts of the vector, one end and the other end. And so head to tail means, let's say I draw the vector A. I'm then going to draw the vector B, starting at the head of vector A. So I'm going to place the tail of B at the head of A, and then the resultant means go from the very beginning to the very end, or A plus B. It means I'm going to connect the very beginning of what I drew, meaning the tail of A, to the very end of what I drew, meaning the head of B. And think of this like you were taking a walk. Let's suppose you walked along the vector A. You start on the tail of A, then you walk to the head of A, but then you don't go back to the beginning. You keep on walking from that point and you continue with B. So the tail of B starts at the head of A, and then your total walk again is from the very beginning of where you started to the very end. Now, vector addition is also commutative, which means A plus B equals B plus A. In other words, instead of drawing A first and then B, now I can draw B first and then A. So let's see how this looks. Here's the vector B, and again, to add A, I'm going to start the A vector at the end of the B vector, and then the resultant, as before, is a vector that goes from the very beginning to the very end. We call that vector b plus a. But if we think about what would happen before, if I draw a parallel copy of a and a parallel copy of b, that was originally a plus b, and we see it gets us to the same point. In fact, you might now see why this is in your textbook or other places sometimes called the parallelogram law. So think about why that's now the name of that law. Now, addition is not head-to-head. What does this mean? Sometimes, for physical reasons, we draw both vectors starting at the same point, and that will be done many times in this class. But that doesn't mean that's the way we're going to add them together. It just means that we might say, oh, there's two forces, for example, at the same point pulling on the same point. But to add the vectors, we still have to use our parallelogram law. What we do is we draw a copy of each vector parallel and put it on the other side. So there's the vector I just popped in parallel to A. There's the vector just parallel to B. And as before, the resultant goes from the very beginning of one of the vectors to the very end of the other vector. So it still has that same resultant that we had before. Now, a common mistake might be that you start with A and B at the same point again, and now you just draw a vector that connects them sort of head-to-head like that one. And I'll just say for now, that is not the resultant of the vector. It does mean something else that you can think about, but that red vector is not the resultant. So don't add vectors like that. Do it like we did on the left. Vector addition is also associative. That means A plus the resultant B plus C equals the resultant A plus B and then plus C. Can you see why this is true? And here again, you might want to take a piece of paper and a pencil and start sketching why that would be true. Think about it. Try it out. Vector addition is also distributive with respect to scalar multiplication. A scalar k multiplying the resultant of A plus B is equal to that same scalar k times A plus k times B. Also try and draw on your paper why you think that's true. Try it out. And finally, vector subtraction, in my view, is best done by adding the negative. So if you're asked to take A minus B, instead of trying to do that directly, it's better to do A plus the negative of B. Think about why this might help you think about it. What have we learned all throughout this lecture? We've learned the basic of addition. So if we convert the subtraction to an addition problem, it follows exactly the same pattern as before. But think about, if you do an example, what the A minus B vector looks like. How does A minus B appear differently than A plus B? That is, could you do an exercise on your paper, take two vectors A and B, draw those two vectors to show their addition, try and then draw those two vectors and show their subtraction. How does it look different?